So we're going to talk about today, we're going to hit our new stuff for the semester now. We're going to talk about ratios. A ratio is a comparison between numbers. For example, if I want to do a ratio, like yesterday, we had two groups in here. If I want to do a ratio of Woods, wow, I can't write today, Woods to broadband students. There were 4 Wood students in here yesterday, there were 3 broadband students. I could write it like that as a fraction. Or I could write it with a colon, like 4 to 3. Or I can even write it with the word 2, 4, 2, 3, like that. Any of those works. And there's even some other alternative ways of displaying it. I like to use the fraction because there's a lot of things we can do with them as a fraction. They're similar to the way we do with fractions. Now there's a big difference that comes out here right now. If that were a fraction, I'd reduce it to 1 1/3. Well, it's not. It's a ratio, so I'd leave it as 2 numbers. I don't want to make it a mixed number. It has to stay as an improper fraction. Now, there's a couple of different types of ratios. This one is 4 to 3. Let's say I ask, rather than saying, let's compare Wood students to broadband students, I want to say, what proportion of the whole are the Wood students? Well, that would be 4 out of how many total? 7. So both of those, when I do this 4 to 3 ratio, both of these ratios is implied here. It's a 4 to 3 comparison of Woods to broadband, but the Woods are 4 out of a total of 7. So let's say, look at one of these tables. Let's do a length to width ratio. So these tables are 72 inches long, and they are 18 inches wide. The inches will cancel out. Both 72 and 18 can be reduced by 18, giving me a 4 to 1 ratio. Now again, if this were just a fraction, I would reduce that to simply 4. But since it's a ratio, I have to leave it as 4 to 1. You'll notice all the units disappeared. So is that 4 inches or 4 feet or what is it? Well, it doesn't matter. Ratios are unitless. So what it's saying is for every 1 unit of length, whether it's 1 inch of length, there would be 4 inches of, 1 inch of width, there are 4 inches of length. Or if it's every 1 foot of width, there would be 4 feet of length. Or if it's 1 centimeter of width, there would be 4 centimeters of length. Whatever units I'm using, for every 1 unit of width, there's 4 units of length. You'll also notice on all the ratios I've done so far, whether here it's students to students or here inches to inches, the labels on both numbers are the same. In a ratio compares 2 numbers with the same labels or same units. So I might have 2 feet to 18 inches. Is that a ratio? Not the way it's written. It's comparing feet to inches. But I can change it. 2 feet can be written as 24 inches. So again, the inches will cancel out. Both 24 and 18 can be reduced by 2 would work, but we can also do 6. So that's 4 to 3. Now again, if that were a fraction, I would reduce that to 1 1/3. But it's a ratio, so I'm going to leave it as 4 to 3. There is something called a unit ratio. In a unit ratio, we make the denominator 1. Now, we don't do that in most ratios. We leave them as just a simple ratio. A unit ratio, we would have to divide out the denominator, dividing by 3. So this 4 to 3 would become 1 1/3 to 1. That's a little bit of an uglier ratio. 4 to 3 is a simpler ratio. So typically for ratios, we leave it like that. What if we're comparing 2 numbers that we cannot make have the same units? For example, let's say we're going to send Tate on a road trip. We're going to send him 365 miles. What's that? In 7 hours. So, we cannot make miles into hours. We cannot make hours into miles. There's no way we can make these the same units. So this is not a ratio. It is a rate. So that is the first big difference between rates and ratios. Rates compare 2 numbers with different units. Ratios compare 2 numbers with the same units. Second, rates are almost always expressed as a unit rate. So what that means here is I would have to divide this by 7 on top and bottom. 7 hours divided by 7 is 1 hour. 365 miles divided by 7 is 52.142857143 miles approximately. Now, we generally would not leave it like that. We would do this. I'm going to round that, of course, like 52.14. And instead of leaving it as a fraction, I'm going to hide the fraction in the units like this, like miles per hour. So the appearance of the fraction in a lot of our rates gets hidden in the units like that. In fact, there are times where we hide the fraction altogether. We might do, let's say that on this trip, Tate gets 26 mpg. What's mpg stand for? Miles per gallon. So 26 mpg really means this, 26 miles per 1 gallon. When we see 26 mpg, we need to think this, because this is the form we need it in to calculate with it. So let's do some examples. Rates are all around us. You saw the miles per gallon, miles per hour. In construction, you might have a truss is designed to hold 60 pounds per square foot, PSF. So what that is saying is for every square foot, it's capable of holding 60 pounds. You might have your density when you're looking at strength of wood and stuff like that. You have standard wood strengths, and then you will adjust the strength using wood density. So density, again, density might be in pounds per cubic foot. Like a lot of your wood is between 40 and 70 pounds per cubic foot. So you might have this particular piece of wood is 52 pounds per cubic foot of density. Another rate that's probably going to be important to you. Let's say you get offered your first job. $19 per hour. A wage is a rate. You might have a boss that expects you, if you're doing roofing, to be able to lay 3 square shingles in an hour. That's a rate. Ratios. Some common ratios that are important. We're going to draw some pictures here, so you're going to have to use your imagination. Any guesses? Gears. We're looking at gear ratio. And in a gear ratio is the number of teeth in the driven gear with the number of teeth in the driving gear. Well, I can count the teeth here. How many teeth does a big gear have? 12 of them. Good. How many teeth in the little gear? 8. How do I know which one goes on top and which one goes on bottom? Well, I need a little bit more information than what I've given you here so far. If I do this, pretend that looks like a little electric motor on that gear. Now, if I separate these gears, which one will stop turning? The 8. So that is the driven gear. It is being forced to turn. It is being driven by the other gear. The driving gear then is the 12. So it's 8 to 12, and of course that reduces to a 2 to 3 gear ratio. Both of those can be divided by 4. So we have a 2 to 3 gear ratio. Now the purpose of counting the teeth on the gears is to just define the size of the gears. If 2 gears mesh together, the distance between the teeth has to be exactly the same from one gear to another. What we really were interested in was the diameter of the gears. The problem is, since the teeth mesh together, where do you measure the diameter at? Do you measure it the outside of the teeth, the inside of the teeth? Well, you measure it, it's called a working diameter. It's measured somewhere in the middle of the tooth. It's the diameter of the pitch, or diametric pitch. So, if we have a pulley system like this where there are no teeth, rather than counting teeth, we measure their diameters. So let's say this is 4 inches and 10 inches. We still need to know which one has the motor hook to it. So now, which one goes on top? The 10. If I cut that belt, the 10-inch pulley will stop turning. It is being driven by the belt. Which pulley is driving the belt? The 4-inch. So the inches cancel out. That reduces to a 5 to 2 pulley ratio. So those pulley ratios and gear ratios not only describe the size of the gear, they also describe the ratio of the speeds of the gear, the RPMs of the gear. They describe the ratio of the torque in each of the shafts. There's a lot of different things that those gear and pulley ratios will apply to. So anyway, let's take a look at another one. Oh, since we're having fun drawing, let's keep going. Any guesses? Pistons, yeah, cylinders. Compression ratio. So, compression ratio is the expanded volume over the compressed volume. Let's say that this is 60 cubic centimeters above the cylinder when this is the minimum volume above the piston, what they call top dead center in an engine. And let's say this is 480 cubic centimeters, the maximum volume above the piston. It's called bottom dead center. This is 480 cubic centimeters over 60 cubic centimeters. Cubic centimeters cancels out. Both of those are divisible by 60. Give us 8 to 1. Compression ratio is usually expressed as a unit rate or unit ratio. So even if it doesn't come out perfectly, a lot of times you do force it to do like a 6.5 to 1 or 7.25 to 1 or whatever. You usually do force that one to be a unit rate. Grade is a ratio. And grade is usually expressed out of 100. So let's just say this is 100 feet here, and this rises 6 feet. That's what they call a 6% grade, or a 6 out of 100 grade. 6% doesn't sound like much, 6 feet and 100. But if you go over by St. Croix Falls on Highway 8, where it gets the steep hill, anybody know what grade that hill is? Section 8. Yep. I think 9 is the steepest you're allowed to go for a state highway. I know a freeway, I think it's 6 or 7 is the steepest they're allowed to go. So, I mean, that seems like a small number, but is it relatively steep? For you guys, there's two of them that are very important. Discussed those terms at all yet? Slope, pitch. Do you know what the difference is? So let's say we got a roof here that's got a 24-foot span and a height of 6 feet. Pitch is height over span. So what's the height? 6 feet. What's the span? 24 feet. That reduces to a 1/4 pitch. It's a 1/4 pitch. Slope is rise over run. So the rise is still 6 feet, but the run is only that much. Half the span. It's 6 feet over 12 feet. Usually slope is given as out of 12. It's actually inches of rise per foot of run, or per 12 inches of run. So that would be a 6/12 slope. Why is there a difference between pitch and slope? Pitch dates back to when you did mostly beam and rafter roofs. So let's say, here's your top cord or your top plate of your stud wall. Let's say the span of this is 32-foot span, right? And you want to have that 1/4 pitch. Your pitch is telling you how high you set that ridge beam above the top of the wall. A 1/4 pitch means you take a fourth of the span. What's 1/4 of 32? 8. So the top of that ridge beam is going to be set 8 feet above the wall. That's what pitch is for. Slope is for angles. If you're building prefabbed trusses, now of course a 1/4 pitch is a 6/12 slope. This angle that you cut all the cords at and stuff like that, that angle is defined by that 6/12 angle, that 6/12 slope. It's technically the inverse tangent of 6/12, 6 over 12. Gives you those angles that you cut everything at. So it's 26.56 or something like that. 26.6 is good enough. Any questions? One that's going to be, like I said, there's density and there's specific gravity and stuff like that for strength of materials. I'm not going to get into those. One that's important to pretty much everybody as a consumer, the debt to income ratio. So debt to income. Once you guys get out of here, how much per hour do you expect to be making?
Nothing.
Nothing?
No.
Really? Salary? Working for yourself, huh? That sucks. Okay, so the rest of you, other than Tate, how much per hour do you expect to be making? What's that? 15? I'd say 15, 16 might not be a bad estimate. So $15 per hour times, we're going to go times about 200 hours per month. 40 hours a week would be 170 some hours a month because there's a few extra days past 4 weeks. We're going to go 200 hours per month. That's going to give you $3,000 a month. That's a little bit of overtime. That's your income. Now let's look at debts. Now debts, I don't mean rent or gas bills or electricity or anything. That's not debts. Debts are loans or credit cards. Okay, so let's say you get out of school. How many of you have student loans? So we're going to be looking at something on those student loans. Probably, usually like 150 to 200 a month. Let's say 150. We'll keep it reasonable. Car? Okay. So let's say you get out of school and you decide you're starting your own business. You want to have a good work truck, right? How much are you going to spend on your work truck?
Probably $2,000.
2 grand?
On a beater. Yeah. Just to get started. So probably, I don't know. Maybe, what was that being? About $150 a month.
$150 a month should get you like a $7,000 vehicle.
Oh, yeah?
Yep.
I think it was like 9%.
Oh, so you had a little bit of a credit problem, huh?
That was the
Let's say that you're going to go. Let's say you're going to get a decent vehicle, like a $15,000 vehicle. So you're not getting carried away. That's about $300 a month. Credit card. You have any credit card debt? Really? Ouch. Yeah. Okay. Let's put that at like 300, 400 a month. Let's do this. Let's make it easy on ourselves. Do 350. How's that? Right now, that total is at $800 a month. Every bank, whether you go to savings and loan or a bank or what type of loan you're getting, there's a little bit of a different standard applied. Each region, each part of the country has a slightly different standard. A good rule of thumb is like a 1 to 3 debt to income ratio. People think that your credit score determines whether you get a loan. That's not really true. Your credit score determines what interest rate you get on a loan. So if you have a crappy credit score, you're going to be paying high interest. I'm not going to mention any names, Tate.
That's my first loan.
Yeah. So you're going to pay higher interest if you have a poor credit score. What determines really more so whether you get the loan than the credit score does is your debt to income ratio. If you have less than $1 of debt for every $3 of income, usually the bank thinks you are a good risk. So they'll generally say that you can afford that loan. So unless you have like a really poor credit history, like you've defaulted on like a half a dozen loans in the last 5 years or something, there's a good chance they're going to give you the money. Your credit score then is going to determine what interest rate they're going to throw at you. So anyway, right now, what would be 1 to 3? If I have $3,000 in income, how much debt could I have to get a 1 to 3 ratio? 1,000. Right now we have 800 in debt here. So you want to go buy a house. Now rent doesn't count on that debt to income ratio. That's not a debt. But if you want to go buy a house, a mortgage is a debt. So how much you got left? Right now you got debts of 800. You can go up to 1,000. You got $200. How much of a house are you gonna get for $200? You can get about $45,000 house for $200 a month. That's about it. That doesn't include your escrow for taxes and insurance. That doesn't count as a debt. That's not part of the debt. Now, if you guys have construction experience, you might be able to find a $45,000 house that you can make livable. So anyway, the big thing, this is usually the one that people get in trouble with, is credit cards. You start getting that $200, $300, $400 a month in credit cards, it really tightens it up. It's so hard to get a loan. The other one is the car. I mean, I put 300 in there. That's pretty middle of the road. I have students that walk out of here, they get that first good job, and they want that $40,000 truck. And they can afford it. They can afford it because they're making enough to pay it off. But the problem is they're stuck paying on that truck for 7 or 8 years. And they can't do anything else because they can't get any other loans, because that really, it chews up their whole debt and their debt to income. So, let's let you guys try some of these. These are in the big book. I believe it's page 154. Let me double check here. Yep, page 154 is the ones I want. Page 154, 1 through 31, the odd. I'm going to give you about 10 minutes to work. Now we're going to start lecturing again. The next step then with these ratios, what are we going to do with them? Well, let's say we have a system where we know we need a 3-to-2 gear ratio. And we have a motor with a gear on it already that has 18 teeth. What gear do we need to put on the other device? So we've got the 3-to-2 gear ratio. The actual ratio has to be equal to that. The 18 going to go on top or bottom? Bottom. Motor is the driving, right? To find that missing number, just like we did when we did percents last semester, we cross multiply and divide. 3 times 18 divided by 2 is 27. So the other gear needs 27 teeth. So it's just a proportion. Yep, 3 times 18 is 54. And divide by the 2. It's 27. Or, let's say you have a truss that has a 32-foot span and an 8-foot rise. I want to find the slope. Well, this is 8 feet, right? This is, what's my run? 16 feet. So 8 over 16 is my slope. But remember, I want slope to be expressed as over what? 12. Roof slope's always over 12. You're thinking grade is over 100. So 8 times 12 divided by 16 is 6. That's a 612 slope. You guys familiar with that symbol? Yes. Usually they just use to put the 6. They don't even put the 12 on there. They just like that as a 6 or 612. Or for your debt to income ratio. Let's say your bank says we're going to bump you up to a 2 to 5. You've got a really good credit rating, credit score. You've been a good customer. We're going to extend you up to a 2 to 5. So with your $3,000 income, what's your maximum debt? Where's the $3,000 going to go? Bottom. Find that number for me quick. $1,200. So $1,200 would be your maximum debt ratio. Similar figures. So we can tell these triangles are similar because they have the angles marked. If 2 of the angles are equal, then the third one must be equal as well. If I tell you that this side here is 12 inches, and this one is 6 inches, we'll call that one X inches. Let's say this is 20 inches. This is going to be Y inches. And this one up here is going to be 30 inches. What we want to do is we want to match up the sides. Now, these triangles are both in the same orientation. You know, this angle's in the same spot there. This angle here is in the same. But really what we're matching up the sides is the sides that are between corresponding angles, equal angles. So let's look at this angle right here. Corresponds to that angle there, right? They both have one little arc on them. This one here, I'll put a box around it so the circle corresponds to that one, right? The side that's between them is a corresponding side. So the 30 here corresponds to the 12. The 12 was enlarged to make the 30. So then the final angle here has to be related. Put a triangle there. So we got circle, square, and triangle, right? The 20 here relates to which side of the other figure? The x, because they're between the same two angles, the circle and the triangle angle, right? Triangle angle. Try to say that 4 times fast. And then we have y corresponds to 6, because they're between the triangle and the square angles in both figures. So they're between the same angles. So that's how we know they're corresponding. Now they're not equal, they are proportional. When I enlarged that smaller triangle, all the sides got enlarged by the same factor. They have to. So I know that the 30 corresponds to the 12. Now sometimes I'm asked, can you reduce that ratio? Sure, if you wanted to. You could make that into a 5/2. It would be easier to work with. But you don't have to. I'm going to leave it as 30/12. If I want to find x, where does x go? Top or bottom here? Well, is it linked to the 30 or is it linked to the 12? It's from the same figure as the 12, so it goes with the 12. What's going to go above it? Well, what goes up here has to be linked to the x, and it has to be linked to the 30. It's linked to the x because it's the corresponding side from the other figure. It's linked from the 30 because it's in the same figure. Does that make sense? So what goes there is the 20. So cross multiply and divide. X equals 8. To find y. So we still have 30/12. Where's y going to go? What's that? Top, because it's from the same figure as the 30. What goes below the y?
The 6.
6. We're good. How do I find y? Cross multiply, divide. Y be 15. So y is 15 inches.
I like it.
You like it?
I like it. That's how I say it.
Math is fun. Come on, you know you want to say it. So, Tate has a dilemma. It's your day for problems, Tate.
Welcome to my life.
Tate has a tree in his yard that he wants to cut down. He is not sure if it's going to reach his house. Doesn't want to knock his house down. Well, the sun up here shines down. And I know my angles are going to be a little bit off, but that's okay. On the tree. And cast a shadow. In fact, I'm going to draw this a little bit better. Cast a shadow like that. Tate's sitting here wondering, I wonder how I can figure out how tall that tree is from its shadow. So Tate takes a stick that is 5 feet tall. And he measures, and he holds it straight up. Uses a level to keep it straight. And he measures its shadow. And he notices the shadow of that stick is 4 feet. So now he measures the shadow of the tree, and the shadow of the tree is 52 feet. How do we find out how tall the tree is? The height of the tree. Well, we got the height of the shadows. The 52-foot shadow for the tree compares to the 4-foot shadow of the stick. Right, those are both the shadows. So over here we're going to have the actuals. What do we know for the actuals? 5 feet, top or bottom? 5, that goes with the 4. The 4 is the shadow of the stick, so the actual height of the stick has to go with the 4, right? On top, there's going to be the H, the height of the tree. Cross, multiply, and divide, we are going to get what? H is 65 feet. What do you think? Not so bad?
Well, not now.
Now the question is, how far is it away from the house?
Yeah, I'm not going to tell you. You don't need to know that.
Well, that's
That would just add to the problem, is it gonna hit?
what you need to do is trim all the branches first, and then you're gonna paint.
Or you can just burn the tree where it stands.
Or take a truck and go the opposite way so it falls the opposite.
Or just notch it with the chainsaw.
So anyway, what we've been talking about here is what we call a direct proportion or direct relationship. When one number gets larger, the other number gets larger. Like here, if the object gets taller, the shadow gets longer. That's a direct relationship. There are inverse relationships out there. In an inverse relationship, there's one of two ways to look at it. In an inverse relationship, when one number gets bigger, the other one has to get smaller. So let's say we're looking at a gear ratio here. Look at gears. So we've got that gear with 15 teeth, right? It's turning this gear with 8 teeth. I want to know, this tooth goes with this gear, by the way, not the other one. I want to know if this gear here, the 15 tooth gear, if that is turning at 120 RPM, how fast is this 8 tooth gear going to have to turn? Is it going to have to turn slower or faster?
Faster.
Faster. It's a smaller gear. It has less teeth, but it has to turn faster. The number of teeth is smaller. The RPM is greater. That's the inverse relationship. So there's one of two ways to look at this. The way the textbook does, I'm going to show you the textbook way first. Then I'm going to show you my way, because I think my way is better. They look at the gear ratio here is 8 to 15 or 15 to 8. It doesn't really matter. I'm going to do 15 to 8. Now logic says the 120 is the 15 tooth gear. That would say the 120 should go up here, right? Problem is this a direct relationship? No, it's an inverse relationship, which means the second ratio is inverted. So the 120, even though it's from the same gear as the 15, it's going to go on bottom. Basically, you're flipping the second ratio. So this number here is going to tell us the speed of the 8-tooth gear. So 15 times 120 divided by 8 is 225. So it is still cross, multiply, and divide there. Now to me that is confusing as heck, because when we set up a proportion, I've been pounding it into when we did percents last semester, and I've been pounding it into in the first hour here. When you set up a proportion, what goes here needs to be related to that, what goes here needs to be related to that, right? In a direct relationship, that's true, but this is not a direct relationship. So I choose to not do them this way. I choose to do them this way. A inverse relationship is not a constant ratio. It is a constant product. So you have the size of the gear, 15 teeth, times its RPM, has to equal the size of the other gear, 8 teeth, times its RPM, X. So it's size times RPM. So 15 times 120, 1800, divided by 8, it's 225. Notice it's the same calculation. Here it was 15 times 120 divided by 8. Here it's still 15 times 120 divided by 8. It's just this makes sense. The 15 and the 120 go together. The 8 and the x go together. Inverse relationships are a constant product. But the way your book sets it up is it does do that proportion where it does one ratio and then the other ratio it flips over. We will talk about this a lot more as time goes on. For now, I'm going to get you some homework. On page 163 through 164. 17 through 31, the odds. Deal with direct and inverse relationships.